Hello, everyone. This is Christian. First, I'd like to thank you again for attending our webinar today. The plan is to show you a brief introduction to the IonFlux instrument principle of operation, after which we will continue with our case study. This talk is part of the IonFlux Webinar series, and as part of this series, we've presented data sets related to a number of ion channel targets that were developed both in-house at Fluxion as well as in our customers' labs. So basically, the IonFlux instrument was designed to fulfill the requirements for the next generation automated patch clamp technology. In other words, we've endeavored to deliver a solution that is faster, better, and cheaper with respect to the status quo. Traditionally, automated electrophysiology systems have been integrated with some type of custom fluid handling station. In contrast, the IonFlux is implemented in a plate reader-like format that can be operated both on the benchtop without the need for fluid handling and coupled to a standard fluid handling equipment. It can interface to a number of commonly found fluid and plate handling robots that are typically available in screening labs. In the image, it's shown coupled to a typical TCAN Freedom Evo pipetting robot, where it's operated as a slave to the robotic station. The format means that our units are both easy to operate and simple in terms of having only a few moving parts, which keeps down the need for service. The small form factor and decoupling from fluid handlers also lowers unit price. We have two types of instruments available that only differ in terms of the degree of experimental throughput available. The IonFlux 16 incorporates 16 patch clamp amplifiers and uses an SPS standard 96 well plate format, whereas the IonFlux HT incorporates 64 patch clamp amplifiers and utilizes 384 well plates. They're both fairly economical and provide an easy upgrade path for customers. The IonFlux 16 is price comparable to a manual patch clamp rig, whereas the HT remains significantly below comparable APC instrumentation. The range of experiments possible using the IonFlux platform is wide, as they're able to address both voltage-gated and ligand-gated channels. Another important feature of the system is the availability of temperature control that adds the possibility of performing experiments at physiological temperature, as well as the ability to keep a constant temperature during the experiments in order to reduce variability due to ion channel responses at temperature. At the heart of the IonFlux system is the microfluidic consumable. It utilizes well plate microfluidic technology, a key Fluxion innovation that seamlessly integrates standard SPS well plates with a microfluidic control layer. The platform has two systems, again, that are identical in design with the exception of the number of amplifiers and the plate format used. So we have both 96 well and 384 well plates available. The plates are made utilizing SPS bottomless plates and bonding proprietary polymer material containing the microfluidics to the bottom of the plate. The experimental pattern consists of 12 interconnected wells with 2 trapping regions and 8 compounds. This pattern is the basic functional unit, and it gets repeated across the 384 well plates 32 times. That means that each compound gets 2 reads, and it can generate 256 compounds times 2 reads. That's 512 data points per plate. The 384 well plate again contains 64 groups of cells or ensembles that are being recorded from. The modality of interfacing between the recording and control apparatus and the plate is by using a simple pneumatic and electrical interface. The way that this operates is it basically after plate introduction into the system via a movable tray, the interface comes down and can apply either pneumatic pressure in order to drive fluid flow, or through the electrodes that are dipped into the wells, it can apply a command voltage and record the current across the cell membrane. We have chosen for this instrument to use an ensemble recording modality. What that means is that instead of recording from individual cells, we are recording from sets of 20 cells at a time. So each one of the 64 amplifiers is recording to us, is connected to a set of 20 cells. And the reason we did this is in order to decrease the variability between recordings and increase the success rate of the experiments. Roughly, this doubles the success rate as compared to using single cells. So finally, I wanted to show you a partial list containing a number of ion channel targets that we've worked with at Fluxion and obtained electrophysiology data from. The columns indicate which ones we have obtained initial recordings from, recorded detailed pharmacology to standard compound response, or optimized to have a highly reliable screen. In this particular talk, Juha will be talking about the development of a GABA assay, again, at the Pfizer Sandwich site. And he's going to share with you their experience integrating the IonFlux into their workflow, as well as evaluating a number of different technologies considered in the evaluation of GABA allosteric modulators. Without further ado, we're going to pass it off to Juha.
Hello, everyone from the United Kingdom. I hope you can hear me all right. Thank you to Christian for the introduction. So what I'm hoping to talk to you today about is how we've developed a high throughput IonFlux assay for detecting positive allosteric modulators of the GABA-A receptor. So hopefully everyone can see my laser pointer as well. So just to introduce the GABA-A receptor, it's a liquid-gated ion channel composed of alpha, beta, and gamma subunits, and each of those has a few variants as well. When the receptor is activated by GABA, its natural ligand, you get chloride flux through the pore, which during normal function leads to neuronal hyperpolarization and inhibition of neurotransmission. The subunit composition is important not only for a GABA response driven by the alpha subunit, but also allosteric modulation by the benzodiazepine site. So in order to get good modulation, you need to have the right proportion of the gamma and alpha subunits. It's been shown that therapeutic agents, such as benzodiazepine compounds, can act as allosteric modulators of the GABA response, possibly leading to pain relief through this inhibition of neurotransmission. So previously at Pfizer, our screening was done using a 96-well filter binding assay and planar electrophysiology using the Sophion Q-patch system. Basically, in order to identify new positive allosteric modulators, we tested several technologies to try and develop a high throughput GABA assay suitable for detecting potentiation of GABA responses. For these assays, we've used the Millipore Alpha 1 cell line, and you can see the catalog number there. And we've also used a in-house Alpha 2 cell line. And just to mention at this point, the Alpha 2 is the main target cell line. And Alpha 1 is a selectivity target, as the Alpha 1 subunit activation has been associated with unwanted side effects like sedation. So just to briefly introduce the Q-patch assay. So for those of you who don't know what the Q-patch is, it's a planar electrophysiology instrument with a 40-well plate consumable, so you can record from up to 48 single cells or 48 populations of cells using the HTX format. In our assays, we've only used the HT. We did trial the HTX, but it didn't really provide solutions that we were looking for. The sketch on the left-hand side of the slide shows you what the wells look like in the QPatch consumables. So you have a channel for internal solution with the recording electrode. You have a channel for external solution with the reference electrode, and all cells and liquids are introduced via this external channel. And basically, on the QPatch, the liquids are applied via an 8-pipette robotic system that you can just about see in the picture. And liquids are applied as pulses. So for instance, in our case, in order to pre-incubate a compound or wash off compound, we introduce 4 pulses of 5 microliters. And then in order to obtain this measured response that is shown in the graph in the middle, we apply one pulse of 5 microliters together with GABA EC20 and our positive allosteric modulators. The thing to note here is that because of the way the liquid is applied, you can't control exactly the incubation time. So in our case, for instance, the incubation time is anywhere between 90 to 360 seconds and generally approximately 3 minutes. The QPatch assay does deliver very high quality data, so you can see some recordings here in the middle graph, and then those recordings normalize to a GABA EC20 response, and then each dose here represents the percent enhancement by a specific modulator of that EC20 response. And what we're measuring is that percent enhancement at the top dose in this case. Now, in our case, in our hands with the quality control filters that we apply, for instance, for seal resistance, minimum current amplitude of the reference GABA application, and leak current, approximately 50 to 60% of the recordings are successful, and overall, approximately 30% of the compound recordings are successful. And in order to get statistically significant results in this assay, we have to test the compounds 4 times in 2 separate assays. And what this leads to, as a practical real throughput, is approximately 350 data points per day. And in our case, that equates to about 40 compounds per day. For our purposes, this throughput is too low to support SAR generation. And although the data quality is very high and the QPatch will remain in our screening cascade, we needed to find a higher throughput solution. The other assay that we have running and can provide higher throughput is a 96-well filter binding assay. So this has been set up with flumazenol as the reference compound that will then be displaced from the benzodiazepine binding site. This assay uses our in-house alpha-2 cell line, and the membranes generated from that cell line are very high quality. The KD values, the Bmax values are consistent and good, and the assay is very robust with a very nice Z prime value of 0.65. The 3 graphs on the bottom left of the slide show you some data quality from our dose response assay, and it's very, very nice. Also, our KIs are in the same rank order as the QPatch EC50s. But the main problem with the binding assay is that it doesn't predict efficacy. The graph on the right-hand side shows you on the left-hand axis the QPatch percent enhancement of the reference EC20 GABA response. On the right-hand axis, you have the binding Ki of the compound. And what I hope you can see from here is if you follow the blue line, which is the binding Ki, compared to the QPatch enhancement, you can see that there are some compounds which are very good in the binding assay. They're very potent. However, they have no efficacy, or they could even be negative allosteric modulators. In other words, the binding assay cannot predict efficacy. So in order for us to try and set up a higher throughput functional assay with higher physiological relevance, we wanted to try the IonWorks. And there has been a paper published by Holland et al., which demonstrate that it is in fact possible to record GABA currents on the IonWorks. For those of you who don't know the IonWorks in detail, it's another planar patch electrophysiology system which utilizes the perforated patch method. So the cartoon in the middle shows you a blow-up of one well of the consumable, where the cells lie on the bottom and are pulled into the pores with vacuum underneath, and then a perforating agent such as amphotericin can be applied to obtain electrical access into the cells. And by measuring from up to 64 cells at a time, you can greatly reduce any variability in the assay. However, as an instrument, the IonWorks is not ideal for ligand-gated ion channels such as GABA because of its discontinuous read method. What this means is that the electrode head, which would apply your voltage commands and read your current responses, cannot be present in the well at the same time as your fluidics head, which would introduce your compound. This is shown in panel A of the graph on the right-hand side from a manual patch recording. So ideally, you want to be measuring the peak current response, but on the IonWorks, it is only possible to measure the current response at a minimum of 8 seconds after compound application, which is demonstrated by the first line. The second line shows you what the current amplitude would be like 18 seconds into the current sweep. And this is then translated to panel B of the graph, where the top curve shows you what the peak current amplitude looks like using GABA as an agonist, and the middle curve shows you the response amplitude when using 8 seconds as your measurement point. So you can see that the current amplitude decreases to roughly 70% of the peak response. More importantly, when trying to measure effect from allosteric modulators, in panel C, you can see dose-response curves for diazepam and zolpidem, two positive allosteric modulators that have a very large effect on the GABA responses. And what you can hopefully see is that the assay window here is actually fairly small. And in our hands, we are also looking for partial allosteric modulators, not full effect modulators such as diazepam and zolpidem. So we tried to set up this assay, but unlike the paper by Holland et al., we tried to set up the assay to measure the shift of a GABA EC50 curve instead of a potentiation assay of an EC20 GABA response. The reason why we wanted to do this was because we found that day to day, the EC20 concentration for GABA varied quite a lot. So in order to avoid this variability, we tried to set up an assay where, with a fixed concentration of a positive allosteric modulator, we could measure a shift of the GABA EC50 curve. Now, using this voltage command shown in the bottom right of the slide, we were able to obtain usable current amplitudes of roughly 1.5 to 2 nanoamps. But despite this, as shown by the graph on the left-hand side of the slide, you can't really tell the difference between a GABA dose response in blue or a GABA EC50 curve that's been modulated using two standard partial modulators. The only effect that we can really see is using a fairly high dose of diazepam, and even in that case, the shift is really too small for the assay to be robust. Now, because of this, we've had to abandon the IonWorks assay. The reasons for why we couldn't see more of a shift Well, the theory could be that, one, we can't measure the peak current on the ironworks, but also some of the modulators may change the desensitization kinetics of the current response, and therefore we can't measure that because we're missing the peak response. So as a result of all of this, the ironworks assay was abandoned. So our next choice for a high throughput assay was the flipper membrane potential assay. The graph, the little cartoon in the top left corner, shows you the principle of the assay. So the cells are loaded into 384 well plates and loaded with a dye, which, when extracellular, is bound to a quencher molecule, which prevents the dye from fluorescing. So upon depolarization of the cell membrane, which in our case is efflux of chloride, the dye moves into the cell, it's cleaved from the quencher molecule, and therefore can fluoresce. This can be measured as shown by the screenshot on the right-hand side of the slide. In there, you can see that at point A, we introduce our benzodiazepine modulator compounds. At point B, we introduce GABA, and this is again an EC50 shift assay. So we're introducing dose-responsive GABA over the modulator, and then at point C, we're measuring the fluorescence change. In comparison to the binding assay, the membrane potential assay is more physiologically significant, but it's still not as good as electrophysiology. However, the benefit would be that the throughput offered by the membrane potential assay is true HTS scale, of up to 20,000 data points per day. So on the next slide, we've got some data from this. So if you concentrate on the graphs at the top, the one on the left shows minimum and maximum control recordings from our alpha-2 cell line. And the assay window is good, and Z prime values are actually very good at 0.8. Also, if you look at the graph underneath the top left, you can see that we can differentiate between a GABA dose response curve, partial modulators, as well as a full effect allosteric modulator such as diazepam. So for the alpha-2 cell line, the assay was very good quality. However, if you look at the graph in the middle top for the alpha-1 cell line, the assay window is significantly smaller, and at best the Z prime values were 0.6. So the assay quality parameters were already quite a bit lower. Also, more significantly, we cannot distinguish between a GABA dose response curve or even a shift generated by a full effect modulator such as diazepam. On top of all of this, if you concentrate on the screenshot again, we sometimes saw effects by compounds alone where just introducing one of the modulator compounds would cause an increase in fluorescence in the absence of a GABA EC50 curve. This meant that we didn't actually know what was happening, what was the effect of the compounds, and also the responses became very unpredictable. As a result of all this, we had to abandon the membrane potential assay as well. We could not measure robust responses in both of our cell lines, and also the compounds were having unknown effects on the assay system. This brings us to the IonFlux assay. So just to recap on what Christian said earlier, the benefits for us is that the IonFlux utilizes a benchtop plate reader format rather than a much larger system that is floor standing, and also we are able to record all ion channel types, both voltage and ligand gated. The throughput of the IonFlux HG is higher than the IonWorks Quattro, which at the moment has been our benchmark. So using the IonFlux, we can record easily 5,000 or even up to 8,000 data points per day. Using the ensemble recordings means that we can reduce variability of our responses. The temperature control is very important for us, not only for temperature-sensitive channels, but also just to be able to regulate the temperature at which we measure instead of having to measure at whichever is the ambient temperature. The other real great benefit with the IonFlux is that because of the plate has been set up as a microfluidics plate, the assays are very, very quick. So we can read 8-point dose response assay for 32 compounds in 15 minutes or even faster. Now, this is, shows you some data from a manual patch experiment. And the reason I wanted to show this to you is because the manual patch is considered by more or less everyone as the gold standard assay, not only for the data quality, thanks to the high gigaohm seals, but also because of the flexibility of your compound additions. You can add compounds at different doses, you can wash them off, you can add internal controls, like in this case, for example, we have a diazepam control present, and you can also add several controls. So not only do we have a diazepam control, we also have a 100 micromolar GABA control in order to ensure that we are at EC20 of the GABA dose response curve. And when we set out to develop an IonFlux assay, thanks to the microfluidics, this was the kind of flexibility that we could aim for in contrast to other existing electrophysiology platforms. So just to give you an indication of what our assay looks like in practice in terms of timings. And these are the timings from our day-to-day assays that we run every week, day in, day out. So if we want to load the compounds into the plate manually, it would take about 3 minutes using a multi-channel pipette. Alternatively, the process that we've set up now is to use a plate-mate compound transfer robot, where transferring the internal, the external buffers, as well as all the compounds into the plates takes about 6 minutes per plate, but it's a walk-away operation, so we just leave this going and go and do some other work. After the compounds and the buffers are in the plate, we prime it. This takes about 3 minutes. After the priming, we add our cells, which you can easily prepare during your compounds are being added. We start our protocol, which at the beginning traps the cells, gets them sealed, breaks into whole cell, and this is all done in 1 minute. After that, for our GABA assay, at the moment we're measuring 2 doses per compound per pattern, and the whole assay takes 16 minutes. So in total, within 20 minutes of the plate being inside the instrument, we're measuring 32 compound responses. For each of those compounds, we're getting measurements from 2 cell traps, and we're looking at 2 applications of 2 doses, therefore 4 compound applications. So in 20 minutes, we get 256 data points. However, we're actually applying several more compounds than just measured 4 compound applications. We're adding reference GABA several times. We're adding wash solutions. We're adding 100 micromolar GABA control. So all in all, each of those traps gets 22 compound applications, totaling over 1,400 applications in a plate in 20 minutes. And to then give you an idea of the total daily throughput, initially when we started all the compound prep manually, we were looking at roughly 4 plates a day. At the moment, where our plate-mate process has been optimized and we don't have to worry about preparing the compound plates, we're currently at 8 plates a day. And the data analysis is something that we've had to adapt because of the in-house systems needed some further work to be able to handle IonFlux data. But once all of this is in place, as well as automated compound plate data association, we are looking at a comfortable throughput within a 6-hour working day of 20 plates per day, or for the GABA assay, 640 compounds per day, n equals 1. So this is really a huge step in our throughput in an electrophysiology assay. Just to give you an indication of what the data looks like. So if you just focus first on the fairly small graph on the right-hand side, This shows you some sweeps from basically a stability recording where we applied 5 micromolar GABA several times in one plate. And the way we measured the currents is that we use the green cursor here as a baseline measurement and the blue cursor as our peak amplitude measurement. And then the graph above shows you the delta I, in other words, peak amplitude minus baseline current. So one of the first steps for us to measure success rates is to look at how reproducible is our agonist response. So I hope you can see from these two graphs, from zones 3 and 4, that the reproducibility of a 5 micromolar GABA dose is really very good. Now, in that same zone, I've also then run a GABA dose response curve to define the EC20 dose to be used in further experiments. So I hope we can also see from zones 3 and zones 4 how nice and reproducible the GABA dose response curve is. So comparing the black and the red traces, those are two different ensembles of cells, and the responses look very nice. So this slide now shows a similar kind of experiment, but in each zone of the IonFlux HD plate, we first run a dose response of GABA, and after that, several applications of 5 micromolar GABA to test for stability and reproducibility. And this is the kind of stability test that we were then doing in order to establish how robust the assay is plate to plate, day to day, independent of cell preparations. So when we analyzed all the data and compiled it, this is what it looks like. So I'm showing here success rates in the graph on the left-hand side from plates 1 to 3. And then I've just typed in the ensemble success rates as well as compound response rates from a further 3 plates. And I hope you can see that the success rates are really quite phenomenally high. So in comparison to 50 to 60% from the Q patch, we're looking at success rates of in excess of 90%. So then, just to show you what the data actually looks like from the experiment that I described earlier. In the graph on the left-hand side, you can see sweeps from one trap of cells. So first of all, we apply GABA EC20. Then we've applied our negative control, which is just DMSO in the presence of that EC20 dose of GABA. Then we've applied a full effect positive allosteric modulator, 1 micromolar diazepam. And then as a final control, we've added 100 micromolar GABA to check that our EC20 dose is within acceptable range of EC20. If I then plot the responses for our reference GABA, negative control, as well as diazepam control, and some compounds from several experiments. So this is these are total responses from 25 experiments using this method. If you look at just the raw current, you can see that there is still variability in the current amplitude from experiment to experiment. If we were to use just the raw current as a measurement, we couldn't tell the difference of compound effects from our negative control DMSO or even our reference GABA. So what we do is that we normalize all responses to the GABA EC20 response. And you can see this in the bottom graph. Now I hope that you can see that our reference GABA applications, when normalized, are really very tight. Our negative control has no effect above reference GABA. We can tell the difference between 2 diazepam doses, and we can also see the difference between different compounds. So this is, again, total data from 25 experiments. Now on the next slide, I hope I can show you the sensitivity of the assay. So this is the graph on the left-hand side shows you a diazepam dose response curve. So this again shows recordings from one trap, and then when combined with recordings of a total of 15 traps, this is what we get as our diazepam dose response curve. The literature value for diazepam, if I remember correctly, the EC50 is 100 to 150 nanomolar, so we're nice and close to that. And also in the bottom graph, I hope you can see the kind of sensitivity and detail from a single experiment. So now we can really see effects from compounds that only potentiate at a roughly level of 20% of the GABA EC20 response. So this is really very sensitive. Just to finally compare the assay resolution of different assay formats, unfortunately I wasn't able to get a dose response of manual patch data, but I hope what you can get from this is that not only is the assay resolution of the IonFlux as good as, if not better than, other assay formats, it actually enables GABA screening at a very high throughput because the IonWorks assay could not distinguish between different modulators in the same way as the IonFlux assay can. The other benefit of the IonFlux system is that thanks to the flexibility of its compound additions, you can run assay formats such as our fast EC50 or cumulative EC50 assay. So here on the right-hand side of the slide, we've applied 1, 3, and 10 micromolar GABA in quick succession without washing in between. And you can then plot an EC50 curve for GABA from this in comparison to your standard assay format. And I hope that the delta I trace on the left-hand side shows you that the repeatability of this type of assay format is also very good. On this slide, I'm showing that previous assay method, but in this case, with a positive allosteric modulator. So we're running, first of all, just the GABA dose response curve, 0.3, 1, 3, and 10 micromolar of GABA. This is the curve on the top. And then in the presence of a positive allosteric modulator, we can see that the responses have increased, and we can actually plot this as an EC50 curve, and now we can measure a shift of the EC50. Now, not only does this give you better data quality because you don't have to worry about the variability of your GABA EC20 dose, but also the assay is significantly faster. So we could read 4-point dose response experiments in the absence and presence of a positive allosteric modulator in 5 minutes instead of 20. So that will again increase your throughput. The other benefit of the microfluidic system is that you can test several things in one plate, several parameters that you would normally be testing in your assay development. So we have practical examples, even today, where we've tested a target with different internal buffers, different external buffers, different cell types, and different cell concentrations in the same plate using different standard compounds. So it really significantly reduces assay development time. And this is a real benefit. Instead of having to spend 2 weeks developing an assay, you might be able to do it in just a couple of days. So to try and wrap up now, really for us, the key advantages for running GABA on the IonFlux, being able to simultaneously add compounds to 64 traps has really reduced our runtime requirements. because we're recording from cell ensembles, our success rates are really very high. And this means that repeat rates for compound screening are low, and the turnaround time for data delivery is very fast. We can apply several compound applications to the same cell ensemble. So not only can we reduce the variability of our agonist recordings, but we can also measure wash-off. We can make sure that we are at the correct EC20 dose of GABA. And we can also add internal controls such as diazepam. The assays are very sensitive, as I've shown you on a previous slide, so we can measure compounds that have 20% modulation, which is really good because sometimes partiality can be beneficial. The fact that we don't have to wait for compound applications, such as in other robotics-based systems, has really increased our assay flexibility. So, for instance, to use that example of how many compound additions we have in our standard GABA assay, doing the same number of applications on different systems would not be possible. Also, the fact that we can co-apply compounds means that we can test new modalities. For instance, the fast EC50 assay that I've shown. Another benefit for assay development is the fact that you can pause the experiments and resume, but in addition to this, you can load new voltage protocols, new compound application protocols. So not only can you test several different buffer combinations, cell combinations, you can also try and see if perhaps your holding voltage could be changed, if perhaps you want to wash your compounds for a longer period. And you can do this all in one plate and in one experiment. So again, significantly reduces your assay development time. The fact that we can test the effective temperature or standardize the temperature at which we're screening, that's really important. That differentiates the system from others that we've used so far. And the fact that you can actually change the temperature within one experiment, again, reduces the number of experiments that you need to run. Just to recap on the throughput. Our binding assay, in practical terms, we can run 80 compounds per day. The physiological relevance of the assay is low because it cannot predict efficacy. The membrane potential assay would have had a very high throughput. The physiological relevance of that would still be low, and the limitation for us is that it only really worked with our alpha-2 cell line, plus we saw these fluorescence artifacts from the modulators alone. The IonFlux assay had a medium throughput, but due to the discontinuous read and the assay format that we tried, this did not work and would not work for similar ligand-gated ion channels very well. The Q-patch assay, the practical throughput is roughly 40 compounds per day. The physiological relevance is very good, it's very high. However, the throughput is too low to support SAR generation, and also we cannot control the compound incubation time, which could lead to discrepancies in day-to-day data. So coming then to the IonFlux HT, the throughput is still medium if you're really comparing to true HDS scale of tens of thousands of data points per day. However, for an electrophysiology platform, the throughput is very high. The physiological relevance is just as high as the Q-patch. As limitations, you might be able to quote that certainly for the GABA assay, where you need pre-incubation of your compound as well as a co-application of compound and GABA, you can only run 4-point dose responses, and the C resistances are low. However, this also applies to the IonWorks, and when using recombinant cell lines, your C resistance isn't as important. And then a very skilled manual patch operator could probably run 2 compound dose responses per day, so that's very low throughput. to thank the people who have been doing a lot of the work. Catherine has been running the Q-patch and the IonFlux. David has been running and developed the binding assay. Kim has been running the binding assay in our department. Vad developed and ran the IonWorks assay. In Pain Research Unit, Julie is responsible for running the Q-patch assays, and Corinne kindly gave me the manual patch data. I would also very much like to thank Neon Zen and Ian, as well as Christian at Flux Science.